So how do we actually deal with these indeterminate forms? Well, we're going to break them down into three different categories. The first of the three different categories is a polynomial divided by a polynomial, which, if you attempt to use the direct substitution property, could yield 0 divided by 0. Now we're going to borrow something from back in pre-calculus that's referred to as the factor theorem. The factor theorem states that if a polynomial function evaluated at a certain value is equal to 0, then x minus that value is a factor of f. Now what this means for us is if you plug in a value and your numerator turns into 0 and your denominator turns into 0, then there is automatically something that you can factor out of both the numerator and the denominator. So you will factor the top and the bottom, and cancel the factor that created the 0. In one of our previous videos, we had a polynomial divided by a polynomial. And if memory serves, this was it. The limit is x approaches 2 of x cubed minus 8 over x squared minus 4. Now, if we were to attempt to use the direct substitution property with this one, we would get 2 cubed minus 8 over 2 squared minus 4. That would be 0 divided by 0. Like I frequently say in French, this is no bueno. However, because I plugged in x equals 2 and was able to get a 0 in both the numerator as well as the denominator, that means that there is a guaranteed factor of x minus 2 that we can factor out of both the numerator as well as the denominator. Now in the denominator, this is a difference of perfect squares, which when I say at parties, or when I go to parties, I like to tell people that factors into binomial conjugates. In the numerator though, this is a difference of cubes. If you don't remember the difference of cubes formula, you're welcome to use a synthetic division to get that the remaining polynomial would be x squared plus 2x plus 4. Now using the theorem from one of our previous videos, we can cancel out the x minus 2's and wind up with the limit as x approaches 2 of x squared plus 2x plus 4 all over x plus 2. Please note that at every single step I'm continuing to write the limit as x approaches 2 until I apply the direct substitution property. As soon as I do that, I can stop writing it as a limit since it's no longer a limit. That numerator simplifies to 12, the denominator simplifies to 4. 12 divided by 4 is 3. So this is the first one of our indeterminate forms. The second one is going to involve radicals. Typically you'll see a radical plus something or a radical minus something in dealing with this. The way that we deal with this is we multiply top and bottom of our fraction by the conjugate of the radical expression. And once again, a conjugate is just a fancy way of saying if they're added, switch it to subtraction, and if they're subtracted, switch it to addition. To give you an example of something like this, we could consider the limit as x approaches 7 of the square root of x plus 2 minus 3 over x minus 7. Once again, if we were to attempt to use the direct substitution property with this, your numerator would be the square root of 7 plus 2 minus 3 all over 7 minus 7, which is 3 minus 3 over 7 minus 7. So once again, the direct substitution property has failed us. So what we will do is multiply. Oh, I guess I didn't need it quite that far down yet. what we're going to do is multiply top and bottom of the big fraction by the conjugate of this expression. The conjugate of this expression would be a radical and a 3 connected instead of by a subtraction sign, by an addition sign. That's the only thing that's going to change when we create our conjugate here. The idea behind this is if you take something of the form a minus b and you multiply it by a plus b, then the result is going to be a squared minus b squared. The squares will cancel out the radical. So this will be the limit as x approaches 7 of the square root of x plus 2 squared, so x plus 2, minus 3 squared. The denominator I'm going to leave as is for the time being. Once you're to this point, what should have happened is essentially you have turned it into a polynomial divided by a polynomial situation and should be able to cancel something out. Please note that your numerator, once you combine all the like terms up there, is now x minus 7. Your denominator also contains a factor of x minus 7. You can cancel those out without penalty, and we're now dealing with the limit as x approaches 7 of 1 over the square root of x plus 2 plus 3. Now, once you attempt to use the direct substitution property, you will have a much more favorable result. Once simplified completely, that will become 1 over 6. So anytime you're dealing with a radical, this would be the way to go. The third and final case that we're going to talk about, let's save some paper, we'll write on the back of this sheet. Third and final case is what I like to refer to as fifth, which is fractions in fractions. The unofficial title for this is Yo Dog, I heard you like fractions, so I put fractions inside of your fractions. The official term for this is a complex rational expression. Oh boy, oh boy, oh, there we go, okay. Complex rational expression. Now the idea is, in a previous math class, you would have talked about how to simplify a complex rational expression. My recommendation is going to be to multiply top and bottom of the big fraction, the lowest common denominator of the smaller fractions. As an example of something along these lines, we could consider the limit as x approaches 6 of 1 over x, or excuse me, 1 over 6 minus 1 over x over 6 minus x. Excuse me. So if we were to attempt to use the direct substitution property, we would wind up with 1 over 6 minus 1 over 6 over 6 minus 6. So your numerator would be 0 and your denominator would be 0. So with that in mind, we take a look at all the little fractions in here and see if we can identify the lowest common denominator. In this case, I see a denominator of 6 and a denominator of x. The product of those would be the lowest common denominator. So next, I'm going to multiply the top and bottom of the big fraction by that lowest common denominator. Now, in the numerator, I'm going to be distributing this through to both terms. If I take 1 over 6 and I multiply by 6x, the 6's will cancel, leaving me with just an x. If I take 1 over x and multiply by 6x, the x's will cancel out, leaving me with just a 6. In the denominator, there's no need to simplify any further, so we won't bother. You'll notice now that your numerator contains an x minus 6 and your denominator contains a 6 minus x. Those are related to each other, but not exactly equal. What I'm going to do is factor out a common factor of -1 from the denominator and call this negative 6x, changing this 6 to a negative and this x to a positive. That's the same as saying x minus 6. This is a very common thing to do when your highest power of x has a negative coefficient. You can now, without penalty, cancel out the x minus 6's. And we're now taking the limit as x approaches 6 of a numerator of 1 and a denominator of negative 6x. At this point, you have gotten rid of the thing that was creating the issue. So the only thing left to do is apply the direct substitution property. Once again, notice that I've stopped writing limit at this step because we've actually applied the direct substitution property. Simplify the result completely and we get negative 1 over 36. There is also the possibility that you could encounter some problems where you have, say, fractions inside of fractions and radicals, or radicals and polynomials. Please feel free to use as many of these tricks as you need to within any particular problem, as many times as is necessary.